So wind is created by the difference in pressure. That is called the pressure gradient force. And with that, wind flows from high pressure to low pressure. We have three forces that we're going to be looking at: pressure gradient force, Coriolis force, and friction. And because of these three different forces, you have certain wind flow around the globe, around the United States, and around high pressures and low pressures. So that's what this chapter is going to be about. Air pressure is the pressure exerted by the weight of the air above. And average air pressure at sea level is about 1 kilometer per square centimeter, or 14 pounds per square inch. Now, in terms of meteorology, we kind of need a consistent pressure so we can get an idea if pressure is higher or lower in a certain spot. Most of our surface weather maps uses millibars, and that's what we're going to be looking at. The standard sea level pressure in millibars is 1013.25. Again, the standard sea level pressure is 1013.25 millibars. So when we're looking at weather maps or we're looking at higher pressure or lower pressure, we can get an idea of which is higher or lower than that. So 1 millibar equals 100 newtons per square, and that's one of the things we look at in the scientific world. But in the meteorology world, we can't do everything in newtons, so we have to convert this over to millibars. So I'm not going to get into the details on how you figure out all the calculations. What I need you to know is the standard atmospheric pressure at sea level. And right now that is 1013.25 millibars. You measure pressure with a barometer. There are different types of barometers. Most of them are just digital right now, but a barometer measures air pressure. When we look at a standard weather map or a synoptic scale weather map, we're going to be looking at standard atmospheric pressure, and you're going to be noticing these things called isobars. Isobars are lines of equal pressure, and that's what these lines are around these high pressures and low pressures in our class notes. So right here you can see 1008 millibars, 1004 millibars, 1000 millibars. So these are lines of equal pressure. So all around this high pressure and all around this low pressure, where you see this black line, that pressure is going to be the same. So lines of equal pressure, that is called an isobar. And that'll give us an idea of where we have regions of higher pressure and where we have regions of lower pressure. So one thing you need to know is that in calm air, there are two factors that largely determine the amount of air pressure exerted by the air mass: temperature and humidity. A cold, dry air mass will produce higher surface pressures than a warm, humid air masses. So typically in the winter, we have higher pressure, and typically in the summer, we have lower pressure. Where you have more energy, where you have more convergence, you have more rising air, therefore you're going to have stronger low pressure systems. Think about tornadoes and hurricanes and thunderstorms, very extreme low pressure systems. They tend to happen more in the summer compared to the winter, as opposed to in the winter we have higher, colder pressure systems. All right, so what are we looking at with the wind? The wind is a result of horizontal differences in air pressure. And so the difference in pressure causes wind. Now, the greater the difference in the air pressure causes a stronger wind. That would be called a steep pressure gradient. So the three pressures we look at are the pressure gradient force, which is the wind that'll flow high pressure to low pressure in the absence of any other forces. Then we have the Coriolis force, which deflects the wind in the to the right in the northern hemisphere. We have the Coriolis force deflecting the wind to the right in the northern hemisphere because the Earth rotates. If you're looking down from the North Pole towards the equator, the Earth rotates counterclockwise. So that force on a rotating Earth deflects the wind to the right in the northern hemisphere. So the pressure gradient force is where it all starts out. The difference in pressure, wind flows from higher pressure to lower pressure. And then at the surface, we have friction. And friction does two things. Friction will slow down the wind and also change its direction. So friction impacts its speed and the direction at the surface. And what will happen is the resultant wind comes out like this. So there's the pressure gradient force, there's your friction, there's your Coriolis force. Now you have different forces at the surface, which includes friction, but above the ground, the upper level wind does not have any friction. So the winds above the ground, we're talking around 20, 30 to 40,000 feet. The wind will flow much faster, much stronger, and flow parallel to the isobars. So what we're looking at here is what we call a geostrophic wind. where we can get an idea of how the wind is flowing if we look at these isobars. So above the ground where there's no friction, wind flows much faster. This is also where we can find the jet stream. So in the jet stream level around 30,000 feet above the ground, the winds are going to flow 100, 150, 200 to 200 miles per hour, maybe even as high in extreme situations around 300 miles per hour. As opposed to at the ground where we have friction, winds are much slower. On average, winds are around 10 to 20 miles per hour. So the three forces that we're looking at, you have the pressure gradient force, where the wind flows from higher pressure to lower pressure. You have the Coriolis force, which deflects the wind to the right in the northern hemisphere, to the left in the southern hemisphere. And then we have friction at the ground. And that friction, again, slows down and changes the speed of the wind at the surface. Now, when you have a very strong difference in pressure, high pressure and low pressure, these orange lines on here are called isobars. Lower pressure here is 980 millibars. Out this way, you have 1,016 millibars. So when you have a very big difference in pressure over a short geographic area, that's where you're going to have what we call a steep pressure gradient. That is illustrated by isobars packed tightly together. So a very big difference in pressure in a very short distance. If you were to follow this isobar that goes into New Jersey, this is lines of equal pressure, so there's not very strong winds here. But if you go horizontally from this low pressure to the coast of Virginia, that's where we're going to be looking at some much stronger winds. Excuse me, a little bit of a cough there. So looking at, again, the Coriolis force. So with a non-rotating Earth, the wind will flow straight from the North Pole right down towards the equator. But we are looking at a rotating Earth, and that wind will deflect to the right thanks to the Coriolis force. Again, if you're looking from the North Pole towards the equator in the northern hemisphere, it deflects to the right, the Coriolis force. Not the left, not the north, not the south, not the east. It deflects to the right in the northern hemisphere. So with pressure gradient force, which is the wind that flows from high pressure to low pressure, Coriolis force, which deflects the wind to the right, and friction, which slows down and changes direction. So it changes its speed and direction on the wind. You get a resultant wind flow, which looks like this when you're looking at higher pressure to low pressure. On a synoptic scale weather map, you get this circular motion here. Wind flows out of high pressure into low pressure. Around this high pressure, which is also called an anticyclone, wind flows in a clockwise motion. Low pressure, which is a cyclone, you have wind that flows counterclockwise, or cyclonic wind flow. Cyclonic wind flow counterclockwise. You can see that rotation around this low pressure system. High pressure, which is an anticyclone or anticyclonic wind flow, flows clockwise. So wind flows out of high pressure into low pressure. And one of the things you will notice is, depending on where you are, because the wind flows into low pressure towards the storm center, it is very important to find out where the storm center is. Because if you're to the east, you would have one wind direction. If you're towards the west of this low pressure, you would have another wind direction, north, south, whatever the case may be. So it's very important to understand where low pressure is, because wind flows into low pressure, and depending on what side of the storm system you are on, you'll have a different wind, and that could lead to different types of wind conditions. So again, cyclonic wind flow, this is all in the northern hemisphere. Wind flows counterclockwise around low pressure. Again, these black lines around low pressure are isobars, lines of equal pressure. And you can see the closer you get into low pressure, that's where we're looking at lower pressure. So it goes from 1,012 millibars, 1,008, 1,004. Remember, the standard atmospheric pressure is 1,013.25 millibars. Now with high pressure, anticyclonic wind flow and clockwise wind flow around your high pressure. Again, these wind flows clockwise around high pressure, counterclockwise around low pressure, is because of the pressure gradient force, the wind that flows from high pressure to low pressure, and then the Coriolis force, which deflects the wind to the right, and also friction, which changes the speed and direction. So it slows down the wind at the surface. Clockwise wind flow here, counterclockwise wind flow with lower pressure. Now, also in the atmosphere, when you have these changes of pressure, where low pressure is and high pressure, you get these things called ridges and troughs. First, let's talk about this ridge where it says ridge axis. This is higher pressure. Wind will flow clockwise up and over the high point of that axis, up and over. So here we have a clockwise wind flow around higher pressure. This would tend to lead to warmer conditions and more stable conditions underneath this ridge. Now, lower pressure, okay, where you have counterclockwise wind flow, this is where you would tend to have stormier weather conditions and cooler or colder weather conditions. Low pressures with a trough, high pressures with a ridge, counterclockwise with the trough, clockwise with this ridge. And these are things that we'll take a look at more in Chapter 7. But one thing you do want to notice that ridges tend to be more sunny, drier weather conditions, and troughs tend to be cloudier and colder. So when we're looking at the surface winds, there's a lot of things that are going on. First, wind flows from high pressure to low pressure. Now we're going to investigate converging and diverging winds. So what will happen here is we have a couple of different graphics, and I'm going to look at this one right here because I think this is the best illustration. With higher pressure, wind flows out of high pressure. That is called divergence. So wind flowing outward from high pressure at the surface, you have divergence with higher pressure. Wind flows into lower pressure, that is convergence. Remember we talked about in Chapter 4, 4 ways to get air to rise, and this is converging. So when you have air flowing into and converging into, then it rises upward. Out of high pressure converging into, low pressure upward, that's where we get rising air. Remember from Chapter 4, when we have rising air, we have condensation, and that could lead to precipitation. So lower pressure is where we find cloud cover and the threat of precipitation, whether it's snow, sleet, freezing rain, or hail. So winds at the surface with low pressure is convergence. Air rises and divergence aloft. Then aloft, that wind flows out of low pressure into higher pressure. And then when you have colder air aloft, you have convergence. Cold air wants to sink now. So that air goes downward, and then we have sinking air. Sinking air means the atmosphere is stable, and you have less clouds and more sunshine. So follow this cycle with me. Air sinking in high pressure, cloud-free generally, lighter winds diverging out of high pressure into low pressure, unstable air. Unstable is warmer, it starts to rise upward, diverges outward, converges into low pressure, and then goes downward. So higher pressure is more stable. You tend to have lighter winds and also more sunshine. Lower pressure, you tend to have stronger winds, rising air, clouds, and precipitation. And now when we look at what happens at the surface compared to above the ground, we can get an idea where we have ridges and troughs above the ground, and at the surface we can find out where low pressures are and frontal features, which we'll talk more about in Chapter 9. So when we get an idea where air is rising, that's lower pressure. That'll show us where clouds are and also where precipitation is. Higher pressure tends to be colder at first and more stable, sinking air, dry conditions. So if you're near a high pressure system, you're going to have nicer weather. If you're near a low pressure system, you tend to have more clouds, stronger winds, and also the threat of precipitation. So when we look at a weather map, this is generally what we look at for a synoptic scale weather map. You can see the low pressure. This is a warm front with the red lines and the semicircles. This is a cold front where we have the blue line and the triangles. So what happens here? We have counterclockwise wind flow around this low pressure. High pressure has clockwise wind flow. So the most important thing about these graphics is understanding that the wind direction is always the direction the wind is coming from. So this is going to be very difficult for some people understanding this concept. So watch this with me. So here's low pressure. So this wind will flow from the south here, hit this warm front, rotate around, and back through. This is Illinois and Indiana here. Here's Illinois, here's Indiana, and rotate around back through this area here, up and around. So with this, you're going to get a certain wind flow along these fronts. We're going to talk more about that as well in Chapter 9. But right now, you get counterclockwise wind flow around low pressure. So if you're near this low pressure, expect clouds, some gusty winds, and precipitation. Now, depending on the temperature, that'll determine what type of precipitation. Remember, we talked about that in Chapter 5. If it's cold enough through all levels, it's snow. If you get a little warm air, you would get sleet or freezing rain. And then if you have all warm air, you would get rain. So we're watching these low pressures. So high pressure here, low pressure here. The difference in pressure causes wind. There's a steeper pressure gradient near this low pressure, so that's why we're looking at stronger winds. Now, if these storm systems are moving, we have a thing called a pressure tendency. So if you're on Long Island, this storm is moving towards you, your pressure will be dropping. If you have a sinking or falling pressure tendency, that would mean you would have lower pressure moving in your direction. That would mean you would have the better chance of clouds and precipitation. If higher pressure is moving towards your direction and your pressure tendency was rising, higher pressure means stable air and better weather. So we're constantly watching the movements of these high pressures and low pressure. Now we use the Cardinal System to get an idea of what the direction is coming from. So there's a couple of ways that we're going to be looking at this. First, most people have heard of a north wind, a northeast wind, a southeast, southwest wind. But in computer models, you can't always use letters, so you need to use numbers. For example, a north wind is either 0 or 360. Going around clockwise, a northeast wind would be 45 degrees. A easterly wind would be a 90-degree wind. A southerly wind would be at 180. A west wind would be 270, northwest 315, and a northerly wind would be 360 or 0. So again, the wind is always the direction it's coming from. So if we had a southeast wind, that would also be known as a wind from 130 degrees. On our weather map right here, you can see these things right here. These are called wind bars. They will give us an idea of what the speed and the direction is. The wind here is coming in from the east, northeast. So the wind east-northeast right here, these winds over areas of eastern Pennsylvania would be a wind between 45 and 90 degrees. Over towards western Ohio into Indiana, this wind right here, that would be a northwesterly wind, roughly around 315 degrees. Below this low pressure system, down towards Georgia, South Carolina, into areas of Tennessee, this wind is coming from the Gulf of Mexico going in this direction. So coming from the Gulf going in this direction, that would be a southwest wind or a wind at 225 degrees. So the wind is coming from the Gulf of Mexico going northward into Virginia. That's a southwest wind. So the wind is coming from the southwest. That's why it is a southwest wind or 225 degrees. So how do we know what the wind is? Well, there's a couple of different ways to measure the wind and its speed. First, direction only is called a wind vane. Wind vane will only measure direction. A lot of times you've seen them on people's houses, in movies, on barns. Some have been witches, some have been fish, some have been sailboats. So you'll see the thing that has north, east, south, and west. A wind vane only measures direction. Now, this little piece of equipment over here, that's called a cup anemometer. A cup anemometer only measures wind speed. So on this weather station here, this information goes into this computer and it lets us know what the wind direction is. And then the cup anemometer lets us know the wind speed. So these are two different devices. One measures direction, one measures speed. A simple device that measures mostly at airports and typically more at smaller airports. There's actually one of these at Republic Airport. It is in the center of the field. It is just to the south of where the Home Depot is on the east side of Route 110 towards the west side of New Highway. So if you ever look out towards the center of Republic Airport near the Home Depot, you will see something like this. This is called a wind sock. It will give you a general wind direction and wind speed. So the more full this is or more rising upward, the stronger the wind. So in this example here, the wind is roughly about 10 to 15 miles per hour. If this was a little bit higher, winds would be more 20 to 30 miles per hour. So a wind sock gives pilots more rural airports a very quick wind direction and wind speed. Most of the equipments that we use now look more like this cup anemometer, which measures speed, and wind vane, which measures direction. And then we have the aero vane. The aero vane will measure speed and direction, and you can see the cable that comes down into the computer that sends it online, and people can read what the speed and direction is. So an arrow vane will actually measure speed and direction. So that's how we kind of measure the actual wind, where the wind vane only measures direction, the cup anemometer measures wind speed, wind sock measures speed and direction, and an arrow vane also measures speed and direction. Also, we have Doppler radar, which can measure and estimate wind speed and direction. So that's one of the things that we look at. We look at how is the wind moving. It's very important to understand the wind flow around low pressure and the wind flow around high pressure. So the basics from chapter 6, as we scroll back up. What are the three forces that make the wind move? First, pressure gradient force, which starts all the wind that moves it from high pressure to low pressure. Then you have the Coriolis Force, which makes the wind move to the right in the northern hemisphere. And then you have what we call friction. Friction at the surface, it is only at the surface, it changes its speed and direction. So with that, we're looking at a counterclockwise wind flow around low pressure and a clockwise wind flow around high pressure. So because of these three wind flows, this is what happens around low pressure, which is also called a cyclone, and this is what happens around high pressure, which is an anticyclone. We're looking at clockwise wind flow with high pressure, and we're looking at counterclockwise wind flow with lower pressure. So when we're looking at the wind flow, we get an understanding of how it's flowing. It flows out of high pressure, which is divergence at the surface, convergence for low pressure, rising air, clouds, unstable air at low pressure, and then you can see divergence aloft. So take a look at the graphics, get an idea of how that wind is flowing. Notice the arrows, outward with high pressure at the surface, inward with low pressure. So that's basically what we're going to be looking at into chapter 6 for today. So I'm going to wrap things up. Make sure you read through the book, understanding what happens. The geostrophic wind is wind that flows parallel to the isobar. The pressure gradient force is wind that flows from high pressure to low pressure. Friction at the surface will slow down the wind, so it changes its speed and direction, and the Coriolis force moves the wind to the right in the northern hemisphere. So those are the weather basics for your air pressure and winds. Study, please, also wind direction and how do we measure wind direction. The wind is always the direction that the wind is flowing from. So if you have any questions, please send me an email and get back to me, and I'll be posting more videos of the chapters. I'm going to do chapter 7, and please log on and go check out the digital login from Pearson. And if you have any questions, please send me an email. So that is chapter 6, understanding air pressure and winds. The difference in pressure causes wind. The greater the difference causes a steep pressure gradient. That means stronger winds, tighter isobars on a weather map. Lighter winds, widely spaced isobars on a weather map would be a weak pressure gradient, and that means lighter winds. So take a look at chapter 6, look at the class notes again, and also read the book. And if you have any questions, please let me know.